Here I will show how to calculate the rotational inertia of a uniform rod. We'll begin with a uniform rod with mass m and length L. Let us look at a small rod element dm that extends length dx along the rod. To find the mass of that element dm, we need to look at the linear mass density, or in other words, how the mass is distributed along the length of the rod. If we denote that linear mass density by lambda, by definition lambda must be equal to the mass per unit length, or simply dm dx. For a uniform rod, however, lambda must be the same for each rod element regardless of its location or size, and therefore we can actually write that lambda also must be equal to the total mass of the rod divided by the length, or m over L. With that, we can see that the mass of that rod element dm must be equal to the total mass over the length of the rod multiplied by dx for any part of the rod. We will use that expression later on. Now, let us see how much is the rotational inertia of the rod about an axis that goes through its center of mass. First, let's draw an axis through the center of mass of the rod and a second axis x along the rod. In that case, the element dm then will extend between x and x plus dx along the x-axis. Because of the smallness of dx, we'll consider the distance from dm to the axis as simply x. The rotational inertia of that small element then, by definition, will be equal to its mass times the square of the distance to the axis, or dmx squared. To find out the rotational inertia of the entire rod, we will need the rotational inertia of all such rod elements. In other words, we will need to calculate the value of the integral of dmx squared. Replacing dm with its value of m over L dx, we get for the integral m over L integral of x squared dx. Now we must determine the limits of that integral. The rod extends half of its length to the left and right of the center of mass axis. And so the limits for x must be minus L over 2 for the lower limit and plus L over 2 for the upper limit. And so what we get now is m over L x cubed over 3 as the value of the integral, evaluated at the lower limit of minus L over 2 and upper limit L over 2. If we factor out m over 3L, we will get in parentheses the upper limit value L cubed over 8 minus the lower limit value of minus L cubed over 8. Or, for the rotational inertia of the rod about an axis through its center of mass, we get the mass of the rod over 3L times 2L cubed over 8. We can simplify this expression by canceling L and one factor of 2 to get the final result of 1/12 of ml squared. Now what about if we need the rotational inertia of the rod about its left end? We will have to start again with the same integral of dmx squared, which eventually will lead to m over L integral of x squared dx. The only difference here now are the limits. The rod will be extending from 0 to L, and so the value of our integral will be m over L x cubed over 3 with lower limit 0 and upper limit L, or factoring out m over 3L, in parentheses we get the upper limit value L cubed minus the lower limit value 0, and for the final, as a final result, we get 1/3 ml squared. Interestingly, we can get that result without integration by using the parallel axis theorem. For that, we will need an axis parallel to the axis to the center of mass that is offset by a distance d from the center of mass, here marked in green. The parallel axis theorem then stipulates that the rotational inertia about the green axis must be equal to that about the axis through the center of mass plus a correction equal to the mass of the rod times the distance d squared. In our particular case, the rotational inertia about the green axis will be equal to 1/12 ml squared plus md squared. If we move the green axis all the way to the end of the rod where it will coincide with the blue axis, d must be equal to half the length of the rod, or it will be equal to L over 2. In that case, for the rotational inertia about that end of the rod, we will get 1/12 ml squared plus ml squared over 4, which again gives us 1/3 ml squared. Not surprisingly, that is identical to the value that we got through direct integration.